Now that we've uploaded the data, we define the workspaces, which are the things that we're modeling. You can create up to 5 workspaces on the one data set. The things that we might be interested in modeling are claim frequency, defined as the number of claims divided by exposure, claim size, i.e. the cost of a claim when it arises, defined as total claim cost divided by number of claims, loss ratio, which is the percentage of premium paid out in claims, defined as claim cost divided by own premium, competitor premium, and competitive position, defined as competitor premium divided by own premium. The higher this value, the more competitive our own premium is. For each workspace, the response variable is what you're modeling, whether it be claim count, cost, or competitor premium. If modeling a ratio, such as a loss ratio or competitive position, then the response variable is the numerator in that ratio. You can have Preddle apply a transformation to the response variable if you want, such as taking the square root, log, or inverse. We won't be applying any transformations to these response variables. You can select a weight variable if desired. If the weight variable takes the value 2 for some record, then the model will apply double weight to that record, as if that record appeared twice in your data. If you don't select the weight variable, then each record is given equal weight. The offset variable can be used in 2 ways. Firstly, for advanced users, you can use an offset if you want to force a particular coefficient into the GLM model. You would need to have this already in the data set. Secondly, and more commonly, the offset is the denominator if you are modeling a ratio, such as loss ratio or competitive position. When used in this way, you need a log transform on the offset. This is potentially one of the most confusing aspects of GLM modeling, but some examples should help clarify. Claim frequency is claims per unit of exposure. So exposure, if it was on the data set, is the offset. If exposure is measured in years, then a policy that has been exposed for 3 months has a quarter unit of exposure. In this example data set, each record is a policy that has been exposed for 1 year, so we don't need an offset for the claim frequency model. Claim size is cost per claim incurred, so claim count is the offset. Loss ratio is claim cost per dollar of premium. Competitor premium is not per anything really, unless it's per policy, but each record is one policy, so no need for an offset. Competitive position is competitor premium per dollar of own premium. When you're modeling a ratio like these, there's a subtle but important difference between the offset and the weight. For each workspace, think about whether the response variable is the ratio itself or whether the response variable is the numerator in the ratio. If the response is the ratio itself, then use a weight but not the offset. If the response is the numerator in the ratio, then set the denominator as the offset and a log transform for the offset. Lastly, we need to set the link function and the error distribution for each workspace. You can read about these in any reference on GLMs and in the help document, but I'll briefly summarize now. If you want to do normal linear regression, choose an identity link and a normal error distribution. If you are modeling counts of some event, such as claim counts, use a log link and a Poisson distribution. If you are modeling the size or severity of something, as long as it is positive, choose a gamma distribution. Statistical purists might favor an inverse link function for it when you're using a gamma distribution, but in the context of insurance modeling, you'll almost always want to use a log link because it gives a multiplicative model. If you're modeling the probability of something occurring, such as a policy renewing, use a logit link with a binomial error structure. Some final advice on workspace settings. If you are modeling a ratio with the denominator in the offset and a log transformation on the offset, as described earlier, then the link function needs to be log as well. The Poisson and gamma distributions need the response variable to always be positive. The normal error distribution can handle positive or negative response values. The binomial error distribution needs the response to be either 0 or 1 for each record, i.e. each record was either a success or a failure. Next we come to the predictors. Each predictor will either be Boolean, numerical, or categorical. Numeric means it was classified as either integer or float upon import. Choose here whether you want to include it or exclude it as a predictor in the model, i.e. will it be predictive of the response in question? We can choose age, garage type, power, sex, vehicle value, and hire car as the predictors. If it's numeric, you can automatically apply a transform, but we won't. Categorical variables are simply either in or out. We can group levels later in the modeling process if warranted, or you can group them pre-upload. Numerical values, either integer or float, need to be banded or binned. The binning is mainly for presentational purposes, so we can later display actual versus fitted values for each bin during the modeling process. We will see later that you can fit numerical predictors as continuous factors or treat bins as levels of a categorical factor if desired. Lower bound, upper bound, and number of bands settings creates evenly spaced bands between the upper and lower bound. For instance, for driver age, setting the lower bound to 15 years old and the upper bound to 90 years old with 15 bands creates the bands 15 to 20, and 20 to 25, all the way up to 85 to 90. As we see, the upload process looked at the range of values in age and pre-populated these settings for us. It pre-populated the 15, the 90, and the 15. But you should adjust these yourself. The chosen lower and upper bounds might not capture all values, so it will also create one extra catch-all band below the lower bound, i.e. less than 15 years old, and another catch-all band above the upper bound, i.e. 90 plus. All bands include the lower bound value but exclude the upper bound of that band. For instance, band 15 to 20 includes the value 15 but excludes the value 20. 20 belongs to the 20 to 25 band. In some circumstances, I actually prefer to ensure these external bands, such as less than 15 or greater than 90, capture some records on the extreme. So I deliberately make the lower bound, the lower band, one step higher than the lowest value. The lowest value then becomes grouped in the catch-all category. For example, if the values span 1 through to 15, I might make the lower bound deliberately 2 and the upper bound 15, with num bands equal to 13. This would create exactly 15 bands for the 15 unique values. The first band will be less than 2, the second will be 2 to less than 3, and then 3 to less than 4, all the way up to 14 to less than 15, and then 15 plus. As a tip, try to set num bands values such that the upper to lower gap divided by num bands, such as 90 minus 15 divided by 15, equals some sensible number, like equals 1, or 2, 5, or 10, etc. If your lower and upper bound values are 2 and 15, such as this, then making numbands 13 would be sensible, but we won't do that for age, for obvious reasons. Once we pick some values here and save the workspace, we can then look at the distribution and then come back and change the bands if needed. Having said that, try to minimize the need to come back and forth, particularly once modeling has started, since whenever you press save, you destroy any models built off these settings. Once you start modeling, you shouldn't need to repress save on this page unless you want to change one of these values shown here, which you shouldn't have to if you invest the time up front to get these workspace settings and the predictor bins correct, which isn't that hard. If you have uploaded several files, you can change between them using this drop-down, but be sure to save any of the changes on screen before you switch data sets, or the changes to the dataset on screen will be lost.